if you were going to model it with a polynomial as opposed to a line, right? What degree might you choose? 3. Why? 2 turning points. Yeah. So we've been talking about polynomial graphs lately, and we said a polynomial that has degree n always has 1 fewer or n minus 1 turning points at most. So if this has 2 turning points, it would have to be at least a degree 3. So degree 3 might be a good choice for this one. So today's class is all about using polynomials to model data. We're going to talk about polynomial regression. So earlier this semester, we entered data into our calculators or GeoGebra and performed linear regression. We got the equation of the line of best fit. Now we're going to see what to do if the data is not very linear, if a line is not a good model. So this table shows the number of women in the full-time civilian labor force in millions that have children under 6 years old for some selected years, 75 to 2000 every 5 years. So we're going to put this data into L1 and L2 and create a scatter plot. T is going to be the number of years since 1970. Okay, so to get to your lists, yeah. I don't. Sorry. You'll just have to take notes. Okay, so we're going to have to enter this data into list 1 and list 2, which, if you remember from when we did linear regression, you go to the stat menu, edit, stat edit. And if you have data that's already in there, you clear it. If you don't have a graphing calculator with you, you can just follow along for now. And when I give you the activity, I'll run to my office and grab my extras. All right, so T is going to be the number of years since 1970. So what am I going to put in instead of 1975? 5. Good. And 1980 would be 10, 15, 20, 25, 30. Nope. Stops at 2000. Yeah. All right, and then my number of women in the workforce in millions is 4.851, 5.866. Oh. Thank you. 7.322, 8.732. And 9.736. Okay, so I would just like to see a scatter plot first. Before I do any regressions, I just want to see what this data looks like. So I go to stat plot, which is second y equals, and I want to turn plot 1 on. So when I have plot 1 highlighted, I press enter, and I have an on-off toggle, highlight on. Then I can just quit out of here and choose zoom 9 was the statistics one. Zoom 9. All right. Anybody have trouble getting this picture? So we've got our scatter plot, and I'm going to fit 2 different models to this scatter plot. We're going to do a regression line, which we already know how to do, and then we're going to do a regression parabola, that is a quadratic equation to fit this data. So to get the regression line, we go stat, calculate, linreg, then we do L1, comma L2, comma Y1, which is under the vars key. Vars, yvars, function Y1. And if you miss any of these steps, because I know I am doing them quickly, at the end of this packet, there is a sheet, how to perform polynomial regression with step-by-step instructions. Okay, so here's our linreg. We hit enter, And it says that my linear regression, ax plus b, is 0.21x plus 3.99. And my r value is pretty close to 1, so it's not a bad fit. So the equation of my regression line is going to be y equals and r squared is 0.959. And I know that when we previously did regression lines, we looked at r and not r squared. I told you ignore r squared. Now that we're dealing with polynomials, we're going to look at r squared because positive and negative association is only relevant when you're dealing with a line. Okay, so now we're just going to look at r squared because we don't care if it's positive or negative. All right, so there's our regression line. Let's take a quick look at what this looks like. If we did everything right, it should be pasted into y1, and you can just press graph and see the best fit line. It's very good at the beginning, right? But as we approach the year 2000, 1990, 1995, 2000, it's not as good of a fit, right? It's close, but it's not as good as it was in the beginning. So I'm going to see what happens if I do a quadratic regression instead of a line. So quit out of here, clear. I'm going to go stat, calc, and instead of choosing linreg, my next option is quadreg for a quadratic regression. And after that is cubic reg and quartic reg, so you can do a 3rd degree or a 4th degree polynomial. That's as high as your calculator will go. You can't do a 5th degree. All right, so we're going to do quad reg, option 5. Same thing you do for linreg. You do L1, comma L2, comma Y. I'm going to put Y2 because I want to keep the line in Y1, and I'm going to put this new regression in Y2. Enter. And it gives me a quadratic function that will be the best fit quadratic to my data. And I have its equation is y equals negative 0.00, let's just round it to 5, x squared plus 0.38 x plus 2.87. Just rounding to a couple of digits here. And r squared is 0.986. So according to the r squared values, which one's better? This one, 0.986, is closer to 1 than 0.959. So this is going to be a better model according to the r squared value. When I go to y equals, I should have magically pasted the quadratic regression into y2. And I'm just going to have this graph a bold line so I can tell the difference between the two. And graph. So there's my data with my best fit line, and here's my data with my quadratic regression. A little bit better. When you go to y equals, to make it bold, put the cursor just to the left of y2 and press enter. And it will change to that little diagonal line will change to a bold line. And then just press graph. All right, so if I want to use the linear and the parabolic, the linear and the quadratic model to predict the number of women who are working with children below the age of 6 in 2011. So 2011 is year X or Y in my models? X, what should I plug in for X? 41, good. Yeah, because I started measuring time in 1970, so this will be 41 years later. So I'm going to go to my table, and I'm going to type a 41 in for X. And I'm going to delete these other things just so they don't confuse you. And I have a y1 value and a y2 value. y1 is the line, and y2 is the parabola, the quadratic. So it gives me two different predictions that are pretty different, right? The line predicts 12.646 million women. Right? And the parabola predicts 10.33 million women. It's like a difference of 2.3 million, right? Pretty big difference. How confident are you in your prediction using the linear model? Not as confident? Why not? Yeah, it seemed to be slowing down. The growth was slowing down. Can you give me a percentage? 95%? Where'd you get that? The R-squared values tell you how confident you can be in the prediction of your regression. So this is about 95.9% confident, but using the parabola, I can say I'm 98.6% confident in that prediction. No, I'm not, because I have the actual data. Yeah, let's see what it is. Let's see, can I make this bigger? All right, 2011, wait, which column is it? The third column, women with children under 6 who are employed. Okay, third column, 2011 is 9.268. 9.268 million is the actual value. 9.268. So the parabola was definitely a better model, right? It came closer to the actual prediction. So using these percentages, I mean, 98.6% confidence is really high, but using a model to predict outside of the data set, like far into the future, is never a very good idea. Okay. So those are not very, I would say, these are too high to use for something called extrapolation, to extrapolate beyond the data set. But the confidence level is something that you would study in a statistics course, and we're not really concerned with putting a real percentage on that right now. All right, we want to use the leading coefficient test to determine the end behavior for each of our models, the line and the quadratic, right? So for the line, what's the degree of a line? 1, and my leading coefficient is positive, so my end behavior is going to be like that. Okay, so right arm up, left arm down. So let's see, for the line, I look like this. And parabola, or the quadratic, it's even degree, which means both arms up or both arms down, but the leading coefficient is negative, so both arms are down. So my quadratic will look like that. Okay. So which model do you think is most accurate in modeling the future number of women in the workforce? I've got a quadratic, I've got neither. The line, all right, we're all over the place here. So there's a good reason, I'm sure each one has a good reason. Can you say why the line? Because the number keeps going up. It does look like in this data that the number just keeps going up. It drops. Yeah, we know based on looking at more data. What the heck? might have to just open it again. Okay, so it's this third column, right? So starting in 1975, it goes up 9839. Yeah, and then it goes down 96. Then it drops. Then it goes really high in 2007, right? What happened in 2007 that might make there be more women in the workforce? Giant recession. Yeah. That was the peak of our recession was 2007. So maybe a lot of women went back to work because to supplement income due to lost jobs or whatever. And then it starts going down again, right? So it maybe doesn't just keep going up forever. So the line would predict that it just keeps going up forever and ever and ever. But there's only so many women, right? So it can't just go up forever and ever and ever. But what does the quadratic predict? That it'll eventually go down to 0 and then go negative, right? But that's impossible. So neither of these is going to be good at modeling end behavior. Right. Though I can see how the data might lead you to believe it's the line, because the data I originally showed you, it keeps going up. And the quadratic, though, but when you look at the original data, you also see that slowing down effect that the quadratic has. But then if you keep following the quadratic, it goes way down, too far down. All right, so models can be really, really powerful, but you have to be pretty critical in deciding when it's good to you, when a model is making a decent prediction, and when you have model breakdown. And actually, speaking of the giant recession in 2007, using models too far outside the data set was one major factor of the recession. So I don't know how much you guys know about it, but I'll do my best to explain the little piece that I know. So one major cause of the recession was the housing market crashing, housing values dropping very quickly. And the reason that happened was because mortgages were being given to people who weren't as qualified as they had been in the past. And so basically, people were investing in mortgages. So people had money to invest, and they thought, you know, instead of putting it in a government bond or something where I get a very small rate of return, I'd like to put it in something that's very safe but pays me more money. Of course, right? So people were doing this stuff with mortgages where they would bundle them all together, and then people would invest in these mortgages and make money off of the interest that people were paying on their mortgages. And based on previous performance of mortgages, everyone thought that mortgages were very safe. You couldn't possibly lose money investing in mortgages, right? But then we started giving mortgages to new kinds of people that they didn't used to give mortgages to, people who have had lower credit scores or whatever. And mortgages became less safe, but nobody looked at who we were giving mortgages to. All we looked at was past performance of mortgages. And they went, oh, 98% confidence, mortgages are always going to do well, right? But then people couldn't pay their mortgages. Banks had to foreclose. And those investments tanked, and people had all kinds of money tied up in the mortgage business. So we were relying on models based on past performance and using them to predict the future, always a risky business. So if you want to create a model, they can be very powerful, right? So that's why we use them, but you do have to always look at them critically. Here's 4 steps for the modeling process. Make a scatter plot of the data. Decide whether you think a line, a parabola, or a polynomial of higher degree would be best to model the data. More peaks and valleys, higher the degree you need, right? Or instead of peaks and valleys, maybe I should say relative extrema. More relative extrema, more maxes and mins, more turning points, the higher the degree you're going to need to model that data. Find an equation of your model. Just have your calculator or GeoGebra do that. Verify that your equation has a graph that comes close to the points in the scatter plot. Look at the graph, right? If it doesn't, check that you made a see if you made a mistake, and if you didn't, then maybe go back to step 1 and say, oh, I guess that wasn't a good choice of a model. I'll pick a different polynomial. Step 4 is you can now use your equation to draw conclusions, make estimates or predictions. But keep in mind, end behavior of a polynomial is not always a good model, right? So you have to be careful how far into the future you use a polynomial model. Extrapolation is the word we use for using a model to predict outside the data set. And it's subject to a higher risk of producing meaningless results. So to select a model, which is step 1, you have to decide whether you should use a linear, a quadratic, a cubic, a quartic, or none of these. And here are some criteria. The graph should fit all the points pretty well. Use the simplest model possible. So if you can get away with a quadratic, use a quadratic, right? Even if a cubic has a slightly better R² value. So the model should make sense within the context of the real world situation as well. All right, so I'm going to have you do some work in your groups. I have several data sets. You're going to get some equations that will model the data, and then answer some questions about the model.